Good morning, students. In this video of High Voltage Engineering Unit 2, we are going to see about what are the various causes of breakdown in uniform fields. So kindly go through the video. Thank you.
Hello, this is designed as a revision guide for VCE Physics Unit 3 and it's on uniform electric fields. So with electric fields, it's about action at a distance. Two positive charges will repel each other. In fact, any two similar charges repel, and two opposite charges attract each other. And you may be familiar with that, but there is a space in between these two charges where there is an electric field. And we're going to talk about how electric fields apply forces on things. So while you may be familiar with that kind of action at a distance, let's just look at how we define a uniform electric field. If we take two charged plates, and we can charge them by connecting them to an electrical supply, so a positive and a negative supply, and supply them with a high voltage, you would probably guess that a positive charge would experience a force to the right, and a negative charge would experience a force to the left. And you may know, of course, that negative charges are attracted to positive and repelled from negative charges. Now, we can explain that in terms of an electric field. So we've drawn some blue lines here, which are uniformly spaced, evenly spaced, and straight and parallel. And that defines a uniform electric field. In practice, around the edges of two plates, you'll get a bit of curving away from the plates. In fact, in order for you to have a completely uniform field, then these plates would have to be very long indeed. But the definition of an electric field line is a line which points in the direction of force that a positive test charge would experience. So here's a positive test charge. And note the field lines can never cross each other, and they're always at 90 degrees to the surface which they come from, and they always move away from the positive and towards the negative plate because their direction that a positive test charge would experience a force. And you might think, what would be the size of that force? Well, it's going to depend on how big the charge is, and it's going to depend on how strong the electric field is. So the formula for force on a charge is Q multiplied by E, where Q is the charge on the particle and E is the electric field strength. The electric field strength is given units newtons per coulomb. If we rearrange this formula, you could define it as electric field strength is force per unit charge. So its units would be newtons per coulomb. It's also possible to think about the electric field strength in terms of how big a voltage you apply to these plates and how far apart they are. You'd imagine that two plates that are much closer together would have a stronger electric field. And so D, the separation of the plates, is on the bottom of this equation. And V, the voltage, is on the top of that equation. And these two things are equivalent. F over Q is equivalent to V over D. And you can show that those two units are the same. In fact, let's just take these two equations and equate them so that F over Q is equal to V over D. With a little bit of algebraic manipulation, we can multiply by D and multiply by Q, and you get F multiplied by D equals V multiplied by Q. One of these terms you may be familiar with, force multiplied by distance, is work done. And so we can replace force times distance with work, and we get the equation work done is charge multiplied by voltage. And you will have come across this in the VCE in the first unit on electricity. We can make a further substitution if we like, rearranging this equation to make the voltage is given by the electric field multiplied by the distance through which we've moved in that electric field. And so replacing V with ED, we get work done is Q times E times D. And that means that the amount of work done on moving a charge in an electric field depends on the strength of that charge, the strength of the field, and the distance that we move it. We'll just do a quick example calculation. If we take an electron between two plates 8 centimeters apart with a potential difference of 800 volts across them, what force would the electron experience? Well, to start with, we'll calculate the electric field strength using V over D. So that's 800 volts over 0.08 meters, gives an electric field strength of 10,000 volts per meter. Now we can calculate the force on that electron. We know the charge on the electron and the electric field strength. So the electronic charge multiplied by the field strength gives a force 1.6 multiplied by 10 to the minus 15 newtons. The question then asks how much work is done on the electron in moving it across the plates. You can use work is charge multiplied by voltage to give 1.28 times 10 to the minus 16 joules. Or we could also use the equation that we derived on the last slide. Work is QED. And of course, you should get the same answer that you did here. So these two equations are, of course, equivalent. So in summary, like charges repel and opposite charges attract. Electric field E points from positive to negative, and it can be defined as the force per unit charge, i.e. a region where charged particles experience a force. And there's a uniform field between two plates which depends on the voltage and the separation of those plates, given by E equals V over D. We can derive an expression for the work done on a charge, W equals QED, or Q multiplied by V.